In this video, we're going to talk about the diagonalization theorem. So I want to begin by just recalling a definition from my last video. So let's recall that a matrix A that is square, so n by n, is called diagonalizable if it can be written in the form where A equals P times D times P inverse. For some matrix D, that is a diagonal matrix, and some matrix P, that is invertible. Okay, so the diagonalization theorem, is a theorem that'll tell us a condition that'll guarantee that our matrix is diagonalizable. So here's the statement. So an n by n matrix A is diagonalizable if and only if A has a basis of eigenvectors. So what it takes for my matrix to have a basis of eigenvectors is we need, because A is n by n, we would need n linearly independent eigenvectors. So if we go about our method of finding the eigenvectors, if we are able to get n linearly independent ones, it turns out that our matrix A is diagonalizable. And in that case, if our matrix is diagonalizable, then the matrix D, it turns out, is a diagonal matrix where the diagonal entries are the eigenvalues. And the matrix P, this invertible matrix P, is a matrix whose columns are the corresponding eigenvectors. So for example, V1 is the eigenvector for lambda 1. And then V2 would be the eigenvector for lambda 2. And Vn would be the eigenvector for lambda n. So those are what the columns of P are. They're the eigenvectors. The entries of D are the eigenvalues. So I want to give a sketch of the proof. So I want to sketch out the proof of this. Okay, so we're sort of interested in knowing when A has this form, P times D times P inverse. So if I have this equation, I can rewrite this. This is true if and only if. If I multiply the right-hand side of both of these by P, I'll get A times P equals P times D. And then the reason why this is an if and only if is I could go from this equation back to the one that I started with by just undoing that, by multiplying by P inverse on the right. Okay, so now let's try to get a feel for, well, what do the columns of P look like? Well, basically, what do P and D look like? So I'm going to write P in terms of its columns, so I'll call them V1, up until Vn. And at this point, let's say that I don't know that these are eigenvectors. So these are just arbitrary columns. And D is some diagonal matrix. So D has some diagonal entries, which I'll call x1, x2, up until xn. And then everything that's not on the diagonal is a 0. So 0 is above the diagonal, and 0 is below the diagonal. All right. So now what I'll do is, if I look at the equation A times P equals P times D, let's compute both sides and then set them equal and see what that tells us. So if I look at A times P first, so the left-hand side, let me scooch this down a little bit. So A times P. So I'll write A, and then P, let's write it out in terms of its columns. So we said the columns of P, we're calling them V1 up until Vn. And then when we first learned how to multiply a matrix by another matrix, the definition was you multiply sort of the columns are going to be A V1 up until A Vn. So it's basically like the matrix A multiplies each of these vectors, the V1 up until the Vn. But this was the original definition of matrix multiplication before we learned that row-column rule. Okay, so that's what AP is, the left-hand side of this equation. Now let's do the right-hand side. Let's do P times D. So for P times D, let me give myself a little bit more room for this one. So P times D. So the matrix P has the columns V1 up until Vn. And then D is this diagonal matrix whose entries are x1 and x2 up until xn. Okay, and then everything below the diagonal is 0, and then everything above the diagonal is 0. So I want to know what happens when I multiply this out. So what I'm going to do is I'm going to slowly work out what the first column would be. So if I want to know what the first column in this product is, what goes in this spot for the first column, the way I'm going to multiply these matrices together is, so my first column is what I get when I multiply the matrix P times this first column vector here. And the first column vector here has x1, and then it's got zeros all below that. Okay, so the first column would be, it's a linear combination of these vectors v1 up until vn, where the weights of the combination are x1, 0, 0, 0, 0, all the way to the last 0. That'll give me x1 times v1 plus 0 times v2 plus dot 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 plus 0 times vn. And just to recap again, just to review, that's what I get if I multiply this matrix P times this first column vector, because that's what the first column in the product should be. And so this just leaves us with x1 times v1. That's what the first column here is, x1 times v1. And if I keep going like this, the next column would have been v2 times x2. And the last column is going to be xn times vn. That's what the last column is going to be. All right, so we need A times P to be equal to P times D. In other words, we need this green matrix and this purple matrix to be equal, which means their columns better be the same. So these two columns better be the same, and all the way to the last two columns better be the same. So let's go ahead and write those equations out. So this means in particular that A times V1 equals x1 times v1. That's what I get from setting the first columns equal. And if I keep going like this, I get, from the last columns being equal, we get A times vn being equal to xn times vn. Okay, so this is sort of looking eigenvalue, eigenvectory. So there's a key observation I need to make to actually see that these vectors, these vi's, are eigenvectors. So remember that the matrix P that we started off with? Well, we need that to be invertible. And if that matrix is invertible, that means its columns, the columns of P were V1 up until Vn, the columns are linearly independent. And if they're independent, at the very least, that means they're all non-zero. So all of these columns they all have to be non-zero. They're all non-zero because they're linearly independent. And that is the condition, that is the extra condition that we needed for something to be an eigenvector. Aside from the fact that we have to have an equation that looks like this, these vectors, so this vector that's showing up on both sides, has to be non-zero. Now we know that it is. So this is an eigenvector. V1 is an eigenvector. In the same way, all the way up until Vn. Vn is an eigenvector. And that means that the numbers, these coefficients that are in front of them, so this number x1 right here is an eigenvalue. This is an eigenvalue. So if we wanted to, we could call this lambda 1 for our first eigenvalue. And similarly, xn is an eigenvalue. This is an eigenvalue. So if I wanted to, I could call this lambda n. Okay, so what we now know is that the vectors v1, comma da da da, up until vn is a basis of eigenvectors. So not just was it linearly independent, because there's n of them, it's a basis. And they're eigenvectors because they satisfy these equations that eigenvectors should satisfy. And we also know that they're non-zero because these vectors are linearly independent. So they satisfy the two conditions that eigenvectors should. So the key takeaway of this theorem for our purposes is going to be that if we want to check if a matrix is diagonalizable, what we need to do is find the eigenvectors and see if we get n linearly independent eigenvectors. And if we do, it's going to be diagonalizable. But if we don't get n linearly independent eigenvectors, then it's not going to be diagonalizable. So the next video, we're going to look at some examples.